Hey there, astronomy students. This is Miss Ruark. I was told that I'm a little too soothing on these, so I'll try to be a little bit more peppy. But this is podcast 13.1. We're talking about how stars die. Now, how could you be soothing when we're talking about death? I don't know, but we'll find out. Okay, so the end of a star's life. The end of a star's life. What happens when the star is at the end of its life? Well, it uses all its that was cute, fuel in the star. Gravity wins over. Pressure's not there to push out on the outside of the star, or the push from the inside out, and then the star will die. How does it die? Well, it kind of collapses in on itself. High mass stars are going to die in gigantic explosions. We call those supernovas. And then those less massive stars will die in a less dramatic event. It's kind of sad, actually. And we call those novas. All right, so let's talk about what happens to the different types. So we have red dwarfs. Red dwarfs, okay, looking at the difference in size here and mass here, your red dwarfs are these teeny tiny ones down here on this end, and then you have your giants up here. So the mass increases as we go from here to here. All right, so a red dwarf is going to be the little teeny tiny one. It's a star with less than 0.4 solar masses, and they mix their stuff completely by convection. If you notice here, it's really hard to see, but these teeny tiny ones, they actually mix by convection. I know it's hard to see. They're so small. All right, so what happens here? They will consume their hydrogen slowly and produce helium uniformly. Okay, and it stays mixed up all the way through. Very little hydrogen will be left when they die, and they will not be able to ignite hydrogen fusion shell, and they can't become giants because there's not any hydrogen left, because it's constantly mixing. There's no hydrogen shells on the outside. So they have pretty much a very unremarkable death. Sad face. All right, well, what about the sun-like stars? So the sun-like stars are going to be these other ones here. They're anywhere between 0.4 and 4 solar masses. That would include our sun. That's why we call them sun-like stars. Oh, yeah. All right, so these sun-like stars are going to fuse the hydrogen and helium and expand to become cool giants, right? So they expand to red giants during the burning of the hydrogen phase, and then they ignite their helium and they burn off their helium in the core, and then after that they can't raise the temperature high enough to fuse the carbon, and so they become cool giants. The interiors are not mixed well, so there's a layer on the inside of helium with a layer of hydrogen on the outside that continues to burn. It turns into helium, the helium will then fuse to produce carbon and oxygen, but it won't get any hotter than that. So you have a degenerate carbon oxygen core left on the inside. All right, what happens when we lose mass from stars? So medium mass stars, which are like those stars from our sun, medium mass stars will lose mass due to stellar wind, and the more massive the star, the stronger its stellar wind is going to be. All right, they lose this mass into space while they're giants, and then they will collapse down and become a white dwarf. Nice. All right, more massive the star, the stronger its stellar wind. All right, and then final breaths of sun-like stars is where they become planetary nebula. So this is an example of a planetary nebula, the Helix Nebula. Okay, I don't really think they have remnants of stars with approximately 1 to a few solar masses of the sun. The radii is about 0.2 to 3 light years, and they expand at about 10 to 20 kilometers per second, which would give them their Doppler shifts. They're less than 10,000 years old, so they're actually pretty young, and they have nothing to do with planets, even though it's called planetary nebula. All right, so well, how do they form? Okay, here's another example, the Ring Nebula. Medium mass star becomes a giant and expels the outer atmosphere. Okay, the collapsed star becomes hot enough. It can ionize the gas it ejected as a slow wind, which gets faster and becomes a planetary nebula in 2 steps. Step number 1, the solar winds from a red giant will blow away the cool outer layers of the star. Okay, so step number 1, slow wind from the red giant blows away the cool outer layers of the star. And step number 2, the hot inner layers of the star will excite the gas that remains. So fast wind from the hot inner layers of the star overtakes the slow wind and excites it, and there we have a planetary nebula. Here's an example of the Dumbbell Nebula in hydrogen and oxygen line emission. So it's showing the hydrogen and the oxygen that's being given off. Let's see, what else have we got here? These are often going to be asymmetric in shape, and the reason for that could be due to the way that they rotate, their stellar rotation, their magnetic fields, or their dust disks around the stars. Okay, so two more nebula. Here's our Hourglass Nebula, which is a planetary nebula, very beautiful. It looks like an eye. All right, and this one here is the Butterfly Nebula. Doesn't look like it could take flight, but I could see a butterfly in there somewhere. All right. Oh, some more. Here we have the Egg Nebula and the Cat's Eye Nebula. Is that it? Nope, some more. Here's some more. They don't really have names yet. Okay, too sad, so sad. Okay, so what remains? Hello. Okay, what remains of these sun-like stars after they blow away their outer atmosphere? Well, we have white dwarfs that remain. So the white dwarfs are sun-like stars that build up carbon and oxygen in their core, but they can't fuse the carbon because they can't get the temperature high enough to ignite that fusion. Okay, so what happens? Well, the remaining helium in the outer shells continue to fuse into carbon, which gets dumped into the mass of the core and makes the mass of the core increase. And as the mass in the core increases, the core will collapse even more, and the matter inside of it will become degenerate. Okay, well, when they become degenerate, they have no nuclear fuel, and they cool real slowly, and then eventually become black dwarfs. Ooh, that's sad. Black dwarfs are very cold. We don't want to become a black dwarf. All right. And this just shows on the HR diagram the main sequence stars here. As they burn, they get hotter and hotter and hotter, but then all of a sudden they cool and they shrink, and their luminosity goes down as well, and they become, hopefully, these little white dwarfs here. Okay. We don't want them to become black dwarfs because, well, that's not fun. And plus, black dwarfs are dark places. So, if you add more mass, let's see if I've got that on the next one. All right, so the degenerate stellar remnant has carbon and oxygen in the core. They're extremely dense. 1 teaspoon of this white dwarf material has a mass of about 16 tons. So think about that. If you eat cereal for breakfast and you take 1 scoop of cereal, that scoop of cereal would have a mass of about 16 tons. That would be 16 times 2,000. That would be 32,000 pounds. That's a lot. All right. A chunk of white dwarf material the size of a beach ball could outweigh an ocean liner. Holy cow! Carnival Cruise Line has nothing on that beach ball. Okay, white dwarfs. They have the mass. It's about approximately the mass of the sun. Temperature is approximately about 25,000 Kelvin, and luminosity is 0.01 of what the sun gives off. So they're luminous, but not as luminous, right? Right. Okay. Let's see. I think it's coming up on this slide. Yeah. All right. So low luminosity, high temperature, white dwarfs are found in the lower left corner of the HR diagram, which are right here. The more massive a white dwarf is, the smaller it is. Ooh. All right. The pressure becomes larger until electron degeneracy pressure can no longer hold up against gravity. And white dwarfs with more than 1.4 solar masses cannot exist. Okay. So if enough mass is added to increase it to a solar mass of 1.4, the white dwarf's radius will shrink to 0 and cease to exist. Okay, the reason for that is because it cannot support its own weight from the pressure on the inside, because the pressure or the matter inside is degenerate, and it doesn't have that pressure temperature regulator. Okay, so if the mass is greater than the I'm not sure how to say this, Chandrasekhar limit of 1.4 solar masses. So that's the limit. If it goes any higher than that, it pretty much shrinks to 0 and it's done. All right, well, medium mass stars up to about 8 solar masses can probably lose enough mass to die as a white dwarf, which explains the large number of white dwarfs found out in space. All right, and wow, hey, that's it. So I guess we will pick this up again on the next one. See you later.